In this mini LonTI class, we're going to talk about energy conditions. So most of you do not work on energy conditions, well, except my PhD students. But I think most of you have encountered or will encounter them during your research. So energy conditions show up in CFT, show up in holography. So if you do classical GR or initial value formulation, so they show up in all these different settings. And a lot of times you just kind of take them as assumptions, or somewhere says this is reasonable, and you just kind of put it in. So in this class, we're going to learn more about them, learn for what fields maybe they hold or don't hold, and see what is the difference between classical and quantum, and see kind of maybe how to derive them, if possible, to derive them. So we have 4 lectures. So I'm going to write the plan. So in the first lecture, which is today, we're going to talk about classical energy conditions. In the second lecture, we're going to do an introduction to QFT and curved spacetimes. So some of these things might be familiar, but some of you might not have worked on curved spacetimes, especially if you just taken the flat spacetime QFT, or you might have not seen this kind of formulation. In the third lecture, we're going to talk about quantum energy inequalities. Which is one of the QFT analogs of classical energy conditions in QFT and C1 derivation. And then in the fourth part, we're going to talk about the average null energy condition. And its applications, in particular, some no-go theorems for causality violating spacetimes. So, I mean, obviously, we'll see how far we get, because it's kind of a lot of stuff that could feel probably double the time. So let's start with some motivation for energy conditions. By the way, I want you to stop me anytime you have questions, and also tell me if you can't see something, can't read something, right? And I'm also going to do some poses for questions. So let's start with an equation I think all of you have seen. This is the Einstein equation. And here we have curvature. And here we have matter. So I think the main question that kind of motivates the study of energy conditions is what kind of spacetimes we're allowed to have in general relativity. And actually, Einstein's theory of gravity is pretty agnostic about that. In what sense it is agnostic? Well, let's say I want to construct a spacetime. So I write down the curvature, and then I plug it in Einstein's equation, and then Einstein's equation is telling me what kind of matter I need to create the spacetime. It doesn't tell me if I'm allowed or not. It just tells me, well, you need this kind of matter, and then you can create your favorite spacetime. So kind of solving the Einstein's equation in reverse. So pick the G mu nu, get the T mu nu. That's it. So GR is not telling us about what kind of spacetime, what we can have. It's agnostic about that. So here comes energy conditions. So energy conditions, that's the definition. Are restrictions and contractions of the stress tensor. And this is the definition. So the energy conditions are really restricting the matter contents of your theory. And then if you want to have some restrictions on the curvature, you can use the Einstein equation and go to restrictions on the Einstein tensor. So we use the Einstein equation, we move back to restrictions on the curvature. So now the first question that comes to mind is, okay, are these imposed or are these derived? And it's actually kind of a combination. So at first they were imposed, and then we saw what kind of matter was obeying them, and then the quantum ones were derived. So it's really a mix. So let's see the motivation for getting those contractions. So the first one is to analyze the behavior of gravitating systems. Without specific metric or symmetries. So this was the original motivation for energy conditions, and in fact, the first energy conditions were on the Gemini, the Einstein tensor. So they were not on matter, but they were on curvature. And the kind of modern form of energy condition was introduced in the first singularity theorems of Penrose and Hawking. So what was the breakthrough of these theorems? Well, before those theorems, what we did was having a specific metric or having some symmetries of space-time, and then we said, well, this kind of space-time will terminate in a singularity. In particular, they use spherical symmetry a lot. And then Penrose first and then Hawking came in and said, well, we don't want to have this kind of symmetry. We want to work with a very general metric. But you can't work with a very general metric and say, well, it will terminate in a singularity. You need some kind of condition. And the condition they put was conditions on the Einstein tensor, in particular on the Ricci tensor, as we're going to see. So there, they didn't use any kind of specific metric. They used just this condition, and they said, well, then this system terminates in a singularity. That was a huge breakthrough, because the big question then was, well, do the systems terminate in a singularity only if we have spherical symmetry? Maybe. If we don't have spherical symmetry, maybe we avoid the singularity. But the answer was no. So this was the initial motivation, and a lot of the motivation of energy conditions comes from here. What happens to gravitating systems? The second one is to capture common features of different kinds of matter. For example, the most popular one is the positivity of energy density, non-negativity of energy density. And that seems reasonable for a lot of classical matter. We cannot have negative energy density. And these two things kind of go together, because when Penrose and Hawking wrote the singularity theorems, they imposed these conditions on the curvature, but then they kind of went back to the matter and said, well, do these conditions make sense for matter? And they sort of make sense for matter. We're going to see these conditions they are. But they thought maybe these actually do capture some features of different kinds of matter. In other motivations, people will start from that and say, is my kind of matter, maybe the one I propose, reasonable? Does it obey these energy conditions? Does it have these desirable features or not? So you maybe start from here. And the third one is one we're not really going to talk really in this class, but maybe kind of keep it in mind as an idea for energy condition. I think it's an interesting one. And it's a relation with the stability of the system. And this is connected to this classical mechanics idea that if we have negative energy in a mechanical system, then maybe it can go lower and lower. If we don't have any lower bound and the system is not stable, it will decay to a lower and lower energy. But if we have the bound, then the energy cannot go lower than that, and the system is stable in that way. So that's like the general idea. So there are some efforts to try to connect the energy conditions that we'll talk about with the stability of gravitating system. There's actually not a very good connection, maybe yet. There's some connections, but not exact. But maybe the idea is also that we want to get some stability of the system. So what do we want from our energy condition? What we want is we want it to be weak enough to be valid. So in particular, to be obeyed by more and more kinds of matter, we want it to be weak enough for that. But we also want it to be strong enough in order to prove theorems. It can be too weak, because then we won't be able to prove interesting theorems and properties of the system, as we said. So these two things are always in a bit of a tension. So we're in search for a condition that is obeyed for more and more systems, and we're also in search of proving theorems with those kinds of conditions. And maybe the overarching question is there a condition that is obeyed by all matter, and we can prove interesting things with it? And we don't know the answer to this question, but maybe we can come closer at the last lecture. Are there any questions? No? All right. So let's talk about our conventions, and then we'll start writing some maths. So I'm going to use the Planck unit for most cases. I'm going to put an asterisk here because in some cases I will restore some of these units dependent on what we're doing. I'm going to use the minus plus metric, and we're going to work on n spacetime dimensions unless stated. A lot of these things are for any kind of dimensions. Some of these things change in the number of dimensions. We will mention that. And we will work on a spacetime, which is defined by manifold and metric. We are going to be working mainly with scalar fields. We are perhaps going to see a few other fields, but mostly scalar fields. And we write the action, which is going to be the Einstein-Hilbert action for gravity plus the matter action, which is going to be the action of the scalar field. This is the usual Einstein-Hilbert action. And this is a matter Lagrangian of the scalar field. And we find the stress energy tensor as the variation of the matter action in respect to the metric. And that's the definition of the stress tensor. We will also use the perfect fluid stress tensor. Where the rho is the energy density, the P is the pressure, and the V nu is the field for velocity, where we have the convention that it has near product of minus 1. So this was the general conventions, and now let's start talking about the particular energy conditions. We're going to introduce 4 in this lecture, see their properties, see their physical and geometric formulation, and then see if they're obeyed for certain kinds of matter and how they are. So the first energy condition we're going to see is the weak energy condition. We use abbreviations, so I'm going to use abbreviations. WEC, the weak energy condition. So here we have a future pointing time-like vector. And this is the physical form of the condition. We state that the stress tensor contracted with 2 time-like vectors is always non-negative. So some important features in this formulation. So first of all, this means that it is true at every space-time point. The second thing is that this is true for any time-like vector field. So when it's imposed, it should be true for any time-like vector field. And the two time-like vector fields here should be the same. We have a different condition, actually, that they are different. So what is the physical interpretation of this condition? Can anyone give an interpretation? Sorry, the? Well, not necessarily the rest frame, but moving in any time-like path, basically, an observer should measure energy density that is positive, that is non-negative. So, so the energy density measured by an observer on a time-like tear is non-negative. So it's the most kind of intuitive energy condition because it kind of makes sense for classical matter to have that kind of condition. And if we go to a perfect fluid, maybe I shouldn't write it here because it's long, but I can write it down here. So if we go to perfect fluid, so here I'm going to pick a time-like vector that is convenient to write it down, and that convenient time-like vector will have -1 in the time direction, and then this will be written as rho non-negative. So this is the perfect fluid formulation. Using the Einstein equations, we can move to the geometric form, which is using the Einstein tensor. And that's the geometric form. And what's the interpretation here? Hard to tell. In fact, it's a bit weird that perhaps the most intuitive energy condition in the stress energy form does not have a clear interpretation geometrically. Because a bit weirdly, the Einstein tensor itself in GR does not have maybe a clear interpretation geometrically. There are a few interpretations, but they're a bit involved. They're not that intuitive. So what is this condition telling us? Not much. We don't know. And that's why it's not really used very much, the geometric form. For the weak energy condition, the physical form is used much more. The next condition is a strong energy condition. Maybe I should write a little this border now. Of course, it has its own abbreviation. And let's write it down. So this is in n space-time dimension. It is not defined for n equals 2. And for 4 space-time dimensions, this is t over n over 2. So this is the trace of the stress energy tensor. And it's again contracted with 2 time-like vectors. All right, at first, it looks a bit weird. We don't know where kind of this comes from. So I think all of you have taken a GR class, at least I hope. So I don't know if you've done this kind of derivation of the Einstein equation of the alternative form. You might recognize this expression from the alternative form of the Einstein's equation, the one with the Ricci tensor, not the one with the Einstein tensor. So in the one with the Ricci tensor, this is what appears there. So let me. And in fact, it's the analogous, maybe it's right on the other board. It does come from the analog of Poisson's equation in Newtonian gravity. So Poisson's equation in Newtonian gravity. We have 4 pi g, and we have an energy density here, which I'm going to put a tilde because it's actually not the same thing as the energy density of the perfect fluid that we have. This is a Newtonian energy density. So when we usually try to derive Einstein's equations, we're like, well, what is the analog of this energy density, this classical energy density that appears in Poisson's equation? And what we find is that it's not the usual energy density, and it's not this quantity. It's not the quantity that we might think that would appear. It's, in fact, the quantity that appears here. This rho tilde is analogous to this quantity. This is in 4D now. So it is analogous to this quantity here. And sometimes this is called the effective energy density. So the strange quantity that appears in the strong energy condition is actually has the analog of the energy density in the Newtonian gravity. It's not used very much, though. This is again a form that is not used very much, and you might have never seen it before. What is used a lot more is the geometric form of the strong energy condition, which actually gives us the interpretation of that condition. So let's use the Einstein equation. And you get the geometric form. And if you get the geometric form, is exactly the Ricci tensor contracted with two time-like vector. So what is the interpretation of that? Well, to get the interpretation of that, we need the relativity equation. What is the relativity equation? This equation is derived from the geodesic deviation equation, which you probably have seen. If you want to see, we're not going to do here the full derivation of the relativity equation because it's a little bit involved. If you want to see that in various books, for example, in Wald's GR book in chapter 9.2, you can see a full derivation of the relativity equation. So here I'm just going to state it. So for a time like congruence, with velocity field T mu, parameterized by proper time, tau, we have the expansion of this congruence, that is defined as theta, and it's the covariant, the divergence of T nu, covariant derivative of T mu in the same direction. And this is this expansion is actually telling us the area of the congruence. So whether the congruence is expanding or converging. So let's write down the equation. I don't think it's going to fit in one line. All right, so this is for time-like congruences. And we see we have four terms here that are giving the derivative of the expansion. So the first term is the term we already recognize from the geometric form of the strong energy condition. The second term is the CR of the congruence. And that is about the deformation of the area of the congruence. We have this term with the omega, that is the rotation or vorticity. That is giving the rotation of the congruence. And then we have this term that is the theta square. So often we consider irrotational congruences. So congruences where this omega is 0. This is irrotational congruences. So what happens then? We have three terms. This term is always negative with a minus sign in front because this is positive. This term is always negative because n is larger than 1. This is theta squared. And what's left is only this term that appears in the strong energy condition, the geometric form. So if we have this holding, then we have that the d theta d tau is negative. So meaning our congruence is actually converging, well, or is zero. So it's not diverging. And this is kind of in the heart of a focusing theorem. So, and this is what Hawking and Penrose used for their singularity theorem. So they used the energy condition to tell them what's going on with the congruence, when the congruence converges or the congruence diverges. So really the geometric form of the strong energy condition is telling us whether a congruence of geodesics is converging or diverging. And this, it has its own name. It's called the time-like convergence condition. And I think there's a nice connection with what was said here about matter, even though the matter form is not that intuitive, because the matter form is kind of telling us what's going on with the energy density in Newtonian gravity, so whether gravity is attractive or repulsive, and the geometric form is telling us whether congruence is expanding, is converging or diverging. So this is kind of telling us if gravity is attractive, then the congruence will converge. So I think that's a nice connection in the interpretation. Let's see the perfect fluid interpretation. Yes. Yeah. Oh, this is with the Einstein equation, right? So you have to use the Einstein. When n is equal, no, it's actually for any number of dimensions. Check the Einstein equation, because if you take the trace, then if you take the trace of G is n, and it cancels out actually. So this form is for any number of dimensions. Should I do it? This is for n dimensions, and this is for n dimensions too. Yeah, it's not just for 4. This is just for 4, right? Because we have 2 here. Yeah. Are there any questions? Yes. No, it does not actually. We'll talk about the implications later. Well, actually, when I was reading for this lecture, I found the reason is that maybe at old times, what they called energy condition is actually the null energy condition. And as we're going to see, the strong does imply the null. So maybe that's the reason. But now it doesn't make sense. Yeah. So let's see what's going on at the perfect fluid. So I'm actually going to rewrite the stress tensor. So let's find the trace of the stress tensor. But yeah, click. And And so let's compute the quantity in the strong energy condition. So what I'll get so for the strong energy condition, we have to pick an appropriate time-like vector field. So I pick one that is just in the time direction, and then what we get is this. We have an n minus 2 here, but it doesn't matter, and that the requirement is that this is non-negative. So we have this condition here for the strong energy condition, which is that n minus 1 p. Do I have? Yes, plus n minus 3 rho, correct, is larger or equal to 0, or in 4 dimensions, we have p plus, so rho plus 3p is non-negative. So again, this is not very obvious why this should happen, and in fact, this is violated by a lot of fields. So if you're a little keen with cosmology, do you know one case where this is violated? The perfect fluid formulation? Yes, dark energy, not dark matter, but dark energy. So if you have a cosmological constant, this is violated. So it's one of the conditions that is the easiest to violate. Next, let's see the dominant energy condition. Also has its abbreviation. And there it's actually kind of similar with the weak energy condition, but there's a difference. Here we have two different time-like vector fields, but they're co-oriented, but they're different. So we have the T mu and the psi nu that are co-oriented time-like vector fields. And there's different ways to write the dominant energy condition. So one of them is to assume the weak energy condition. So have the T mu nu contracted with two time-like vectors, plus have the requirement that the vector, this vector is causal. Causal meaning it's time-like, or no, it's not space-like. So this is one formulation. And that has the following interpretation, that the flux of the energy momentum measured by an observer is causal, because this is the flux, and the requirement is that this flux is causal. And if we want to move further with this interpretation, is that the propagation of energy in the form of the energy momentum flux is not superluminal, right? That's what we mean by causal. So no superluminal propagation of energy. So we can write easily the second form of the dominant energy condition using these two conditions together. So this vector being causal, it means that this vector is non-positive, right? It's time-like. Its argument is time-like. So we can put those things together, and what we have is that the T nu sine u t nu is non-negative. So by raising and lowering some indices, this is the second form of the dominant energy condition, where the stress tensor is contracted by two time-like vectors. So to write this form, I use the fact that this is a time-like or null. Right? So assuming that it's time-like, we can write this form. And using the Einstein equation, we have the geometric form of the dominant energy condition, which again does not have a clear interpretation. It involves the Einstein tensor. And it's easy to see that this kind of condition implies the weak energy condition, because if these two vectors are the same, then we immediately have the weak energy condition. Or from this, we just don't have this requirement, we just have this, it implies the weak energy condition. So the dominant energy condition always implies the weak energy condition. So we found at least one implication. Let's see what's going on with the perfect fluid formulation here. It's actually not as easy as maybe the other energy conditions. So I'm going to use the first formulation that I have here, where it's the weak energy condition plus the causal nature of that vector. So for the first one, we know what it is. This is the weak energy condition. So zero. So that gives us the rho is non-negative. And then the other one is a little difficult one. So let's work it out. So what we're doing here is finding the norm of this vector, and we're gonna see we're gonna impose that this is non-positive, this is negative, and then we will get the condition. So let's find the vector first. So in the first term, what appears is the inner product between the fluid's for velocity and the other causal vector. So I'm going to write that as nu dot psi. Maybe it's here. Actually, I'm going to write this as psi mu. So if it's all right, so this vector has two parts. One part is in the direction of v mu, and the other part is in the direction of psi mu. Now let's find the norm of the vector. And we have some cancellations here. All right. So we have two terms now. That one term is the v inner product with psi, and we also have the norm of psi squared. So we know the signs of these things. So we know that this is non-negative, right? For it's the inner product of the vector. And then we know that this is negative because psi is a time-like vector. So I'm going to kind of make our life easier and define the psi mu to be -1, and then have some space-like part like A1, A2, etc. We're in n dimensions. And then it's time-like. So we have this inequality. So and then this is -1. So the inner product with v is the pore velocity of the fluid. So we always take it as -1, etc. So this is just 1. So then what we have is minus rho squared plus p squared from the first term. This is up to n -1. So what we get is that the rho square is larger or equal than the sum of this. All right, so this is for this general thing, but we can see that the maximum one, to obey this condition that xi is a time-like vector, so xi has to be a time-like vector, so this inequality has to hold. So the maximum one is for this sum to be 1. That is the maximum possible one we can have. We cannot have a larger one. So this condition is formulated as rho squared larger or equal than p squared, or rho larger or equal than the absolute value of p, meaning that the energy density is larger than the pressure in any pressure in any direction. Either it's positive or negative. So the energy density dominates over the pressure. There's actually a couple of different ways of doing that, but here I made this particular choice. You see that another interesting thing is that if psi is exactly the same vector as t, we took t to be minus 1, 0, 0. So if we take all the spatial directions to be 0, then we just have rho positive, right? So it's not giving us any new information. So if psi is different, however, we have this different condition. And the last condition to talk about is the null energy condition. So the null energy condition is the same as the weak energy condition contracted with two null vectors. So here Kmu is a null vector field. And for perfect fluid, it gives us that the energy density plus the pressure are non-negative. So what is the interpretation of that? Well, the interpretation seems nice at first. Well, energy density plus pressure non-negative seems a reasonable thing for most fields, etc. But remember that we have a null vector field. So this is for an observer moving on a null geodesic. Do we have observers moving in null geodesics? Not really. I mean, light moves in null geodesics. So it's not really a very satisfying interpretation. So for observers on null geodesics, rho plus p is non-negative. But remember this thing here that we're null geodesics. Regular observers are not on null geodesics. Do we have a nicer interpretation if we go to the geometric condition? Well, we do. So if we use Einstein's equations, we get this form of the condition. And this form of the condition has a very nice interpretation, again, due to the Ricciardo equation. So we have a form of the Ricciardo equation for null geodesics. Let's write it down. It's very similar with the time-like one, but now we have null congruencies. Here, the geodesics are parameterized by an affine parameter lambda. We again have the theta, which is defined in the same way. We have the shear. We have the rotation. And the only difference apart from defined parameterization is how the number of dimensions enters. And here we have n minus 2. So again, for irrotational congruencies, this is 0. And we have the same interpretation. This is negative. This is negative. So if this condition holds, then we have the d theta d lambda now being non-positive, negative, or 0, meaning the congruence of the null geodesics is only converging. And this condition also has a special name. It's called null convergent condition. There's another thing that we should note about this null energy condition. So if we take the time-like vectors, they can go arbitrarily close to null vectors. So if we take the weak energy condition or the strong energy condition, and we move these time-like vectors arbitrarily close to a null vector, then we should get closer and closer to the null energy condition, as continuity suggests. So both the strong energy condition and the weak energy condition should imply the null energy condition. So by continuity, the weak energy condition and the strong energy condition both imply the null energy condition. And that gives an extra condition for the perfect fluid form of the weak and the strong energy condition. So for the weak energy condition, we had that the rho is non-negative, but we also need by continuity to have this in order for the null energy condition to hold. And for the strong energy condition, we had this kind of weird condition where with a number of dimensions. So we had, see if I don't make the numbers wrong. It's 3 n minus 1. It's written here. Perfect. That's kind of have either. Yes. And minus 3 rho. Plus, we need to have this condition. So when we write the perfect fluid form of these conditions, we should always have that extra condition together, because by continuity, we wanted to imply the null energy condition. So let's start with some connections between the four energy condition we introduced. So we have a dominant energy condition that, as we said, implies the weak energy condition, that implies the null energy condition. And then we also said the strong energy condition implies the null energy condition. So these are the connections between the energy conditions. And as Wim asked, actually, the strong does not imply the weak, which is a bit counterintuitive. So the strong does not imply the weak. In fact, it can be cases where either one is obeyed, the other is violated, and vice versa. And something else I wanted to look at is the perfect fluid interpretation of the conditions. So we're going to do some plots where this is the energy density, this is the pressure. So let's look at the weak energy condition first. So the weak energy condition has the non-negativity of the energy density plus the one that comes from the null energy condition, which is the energy density plus the pressure. So let's see what this means. Where is it obeyed? Well, first we're looking at the top half, because the row has to be non-negative. And then also the row has to be larger or equal than minus p. So that introduces a 45 degree here. So this is the area where the weak energy condition holds. Let's look at the strong energy condition. So for the strong energy condition, we have rho plus 3p in 4 dimensions, and plus the one that comes from the null, which is rho plus p. So here we are not looking at the positivity of energy density. In fact, we have rho larger than 3p, so we have not 45 degrees, but 1/3 here. And then from this, we have rho plus p, so we have 45 degrees here. So it's this area where this condition is obeyed. And you can see from these two plots clearly that there are places where the weak energy condition is obeyed, the strong is violated, places where the strong is obeyed, the weak is violated. Let's look at the dominant energy condition. And it's also positive. That comes from the weak energy condition. And so the dominant is only this part. So positive rho, but also it has to be larger than the pressure. So here you can see how the dominant actually implies the weak. It's always obeyed. And finally, we have the neck. So the neck is here, and again, you can see how the strong implies the neck, and the weak also implies the neck as well. Neck. So I think the implications are seen better here. So I'm gonna write a little table to keep here for the next part where we're gonna do some applications. So I will use, I think, the last two boards. So this is the physical and this is the geometric. All right. So the next question I'm going to answer is, why do we have 0 on the right-hand side of the energy condition? And could we have something as, for example, a negative bound? We could have some constant and have like minus that constant. So why are the conditions with a 0? I mean, one explanation is, oh, it's easy. Let's just have it positive. But another explanation is that these conditions should hold, in particular, the three conditions that are with time-like vectors. The weak energy condition, the strong, and the dominant are with time-like vectors, and they should hold for any time-like vector. So let's introduce a tensor. I'll call it S mu nu, where it could be T mu nu, or it could be the quantity that appears in the strong energy condition. And we have the following proposition. I'm going to put two time-like vectors, eta mu and psi mu, and let's say that is larger than a negative bound, which is a finite constant. For any time-like eta mu and psi mu, then the greatest bound is 0. Let's see the proof. It basically has to do with the rescaling of a time-like vectors. So let's define two more time-like vectors. Let's say we have a v mu that is r eta mu, and w mu that is r psi nu, and let r be non-negative. So we're really redoing, we're doing a rescaling of these two vectors. So our bounds should also hold for these vectors. But that should hold as r goes to infinity. Since it should hold as r goes to infinity, then the quantity here should be 0, should be larger or equal to 0. So if we allow for all time-like vectors, then that means we allow the rescaling of these time-like vectors. And if the lower bound should hold for all time-like vectors, including all the rescalings, and take the rescalings to infinity, then the only possible lower bound we can have is 0. However, if we impose our condition to be for unit time-like vectors, then we can have a lower bound. And this is done in some applications. So let's write a little note about that. So if the eta nu and the psi nu are unit time-like vectors, then they can have a lower bound. So note, if you need a lower bound for your application, then you need to write, for example, a weak energy condition with a negative lower bound, then make sure that you impose that condition for all unit time-like vectors and not for all time-like vectors. All right, so now it's time for you to do a problem. I don't know if other people give you problems in LonTI series, but I do. So we are going to apply these energy conditions for the scalar field. Do we have any questions? Something you want me to repeat or? All right. So we're going to look at the minimally coupled scalar field with mass, with a non-negative mass. And this is the stress tensor. And by this notation, I mean this. So this is some dummy index sigma. Or you can use a metric rate. So what I want you to do is to apply this stress tensor to the four energy conditions that we show and see if they are obeyed, if they're not obeyed, and why. All right, so this is a vector that we have, and I'm going to introduce a little shorthand notation. So I'm going to write that as the inner product of psi with nabla phi. That's not necessary, but it makes the writing a little easier. And now let's look at the norm of the vector. And what we have to show is that the norm of this vector is negative, so that it's causal or non-positive. And this is squared, right? So here we take the inner product with a vector with itself. And then we have two terms remain, because we can group them together. The xi, I'm putting them in absolute value because it's negative. The xi is time-like vector. So now both of these terms are negative, and the dominant energy condition is proven. Well, let's unread that. And the last one, let's do the strong energy condition. Whoops. Sorry. I think the board had something. So the dominant, so the strong energy condition, I think some of you also got that one. And it's an important one because unlike the other ones, it is violated. So first we find the trace. And then we compute this quantity. And there's a G mu here. I'll put it here. And there's something nice happening, actually. The terms with the null of phi, so these terms here cancel out. So what we have is this. And that's what you could find in here. And then you have the term with mass. So all of these canceled out. This is the term that multiplies the null line. And so at the end, what you have is these two terms. And the first term is clearly positive, and the second term is clearly negative. So the question is, do we have violations? Can you think of a case where we do have a violation, where the second term is clearly larger and negatives on the second one than the first one? Can you think of a case? Constant field, exactly. When the derivatives, these derivatives are zero. And that doesn't happen only for a constant field. That doesn't depend on time, for example. But it also can happen at some random point, right? So when this time-like derivative of the field is zero, then the strong energy condition is violated. So in a regular spacetime with a minimally coupled scalar with a mass, we will always expect to find some point where the strong energy condition is violated. So we see that even in this simple case, the three energy conditions are obeyed, but the strong energy condition is violated for this field that has mass. For the massless field, it is obeyed because this term goes away and we just have the first term. And I would like, I had a little more, but I would like to give you some homework. And this is a more complicated stress tensor, so let me write it down. So this is for the non-minimally coupled field, because we're not going to do it next time. So this is the following stress tensor, and I will show you where it comes about. So this part is pretty similar, but then we have an extra part that depends on this psi, that is a coupling constant. And we also have the curvature. We have the Einstein tensor here, because the Lagrangian that this one comes from is different than the Lagrangian of the regular scalar field. And it includes terms with the mass, but also it includes a term that depends on the coupling with the curvature. So it includes a term where the Ricci scalar is coupled with a field with a coupling constant psi. What is this coupling constant psi? Well, exactly the constant that couples these two fields. There is also an interesting exercise. There's a particular value of psi. Do it without a mass. So forget mass, and look at what kind of value of psi do we need to have conformal coupling. Meaning, if we transform the metric and we transform the field, for what value of psi is the whole Lagrangian conformally invariant? There's a particular value of psi for this that happens. If you're impatient and you want to read about it, Wald in an appendix for conformal coupling has that. Now, for the energy conditions, if you look at this stress tensor, I want you to check only the null energy condition. And the null energy condition is in fact violated, and it is violated for particular values of phi, but it is violated. So this is one case where all the energy conditions are actually violated. All right, let's eat pizza.